You know that moment, you walk into a dark room, you flip a switch, and boom, light. It feels so simple, almost like magic. But what if I told you that simple flick of a switch is the very last step in a massive, incredible journey? Today, we're going to follow that journey from the outlet in your wall all the way back to where the power is born.
So, let me ask you a question. When you plug in your phone at night, where does that power actually come from? I mean, really think about it. For most of us, it's just there. But the real story is so much cooler.
So let's do it. Let's trace the path of power. We're going to start where it all begins, inside these huge power plants. And we're going to follow that electricity as it travels hundreds, maybe even thousands of miles, just to get to you. All right, first stop on our journey, the birthplace of electricity, the power plant. This is ground zero for pretty much all the power we use. But how do they, make it? Well, it all boils down to one really important idea. And that idea is called energy conversion. See, you can't just create energy out of nothing. It's impossible. So power plants are basically masters of transformation. They take one kind of energy, like the heat from burning coal or the powerful motion of wind, and they convert it into the electrical energy we need.
And when it comes to power plants, there are really two main families. On one hand, you've got the ones that burn stuff, fossil fuels like coal and natural gas. And on the other hand, you've got renewable plants that harness the power of things that don't run out, like the sun, the wind, or rushing water. But no matter the source, their goal is exactly the same: convert that energy into electricity.
Let's take a classic power plant that burns fuel. The idea is actually pretty straightforward, even if the machines are gigantic. Step 1, you burn a fuel to get it incredibly hot. Step 2, you use that heat to boil a ton of water. Step 3, that creates the super high-pressure steam. And step 4, you blast that steam at a giant pinwheel-like machine called a turbine, forcing it to spin like crazy. Now that spinning machine, that's what's called the prime mover. And it is the critical link in this whole chain. It doesn't matter if it's a steam turbine, a giant wind turbine, or a water turbine inside a dam. Its job is always the same: take some form of energy and turn it into pure, powerful, mechanical motion. So right now, we've successfully turned our fuel source into rotation. Okay, so we've got motion, a huge shaft spinning incredibly fast. But how does spinning turn into electricity? For that, we have to go right into the very heart of the power plant. And this is the generator. This is where the real magic trick happens. A generator takes that spinning mechanical energy from the prime mover, and using the incredible power of magnets, it converts it into electrical energy. And it really just boils down to two main parts. You've got the rotor, which is the part that spins. Just think of it as a huge spinning magnet. And then you have the stator, which is the stationary part on the outside, wrapped in miles and miles of copper wire. As that spinning magnet, the rotor, flies past all those wires on the stator, it gets the tiny electrons in the wire moving. And guess what a flow of moving electrons is? It's an electric current. It's that simple and that powerful. So we did it. We've made electricity. But it's stuck at the power plant, which could be hundreds of miles away from where you are right now. So the next leg of our journey is all about getting it there. Welcome to the high voltage highway. Here's the thing, you can't just send electricity down a regular wire for hundreds of miles. You'd lose most of it as wasted heat along the way. To do it efficiently, you have to crank up the voltage, like way up. We're talking hundreds of thousands of volts. And the unsung hero that makes this possible is the transformer. This piece of tech is absolutely essential for our modern world. It can raise or lower the voltage of electricity almost perfectly with very little power loss, which lets us customize the electricity for every single step of its long journey. So think of it like this. As the power leaves the plant, it immediately goes through a step-up transformer. This jacks the voltage way up, getting it ready for its long-distance trip. Then, as it gets closer to our towns and cities, it'll go through step-down transformers that bring the voltage back down to safer, more useful levels. And you've seen this stuff everywhere, right? Those gigantic metal towers marching across the landscape with thick wires straight between them. Those are your transmission lines. That's the superhighway of the grid. And those fenced-in areas full of weird-looking equipment, those are substations. They're basically the off-ramps and interchanges for all that power. Okay, we've successfully moved our electricity all the way across the country. We're on the home stretch now.
This is the last and most important part of the trip, getting that power from the main grid safely into your house. This is the final mile. This is the job of the distribution system. So if the transmission lines are the huge interstates, think of the distribution system as all the local streets and roads that branch off and wind through your neighborhood. These are the familiar power lines you see running along your street.
So at a local substation near your home, that high-voltage electricity takes its last big step down. Transformers lower it to a much safer level that's perfect for our appliances and electronics. From there, it travels down those local lines, through a meter on the side of your house, and finally, to the socket in your wall. Journey complete.
But hold on, there's one last piece to this giant puzzle. And honestly, it might be the most complex and amazing part of all. I mean, making electricity and sending it to you is one thing, but doing it perfectly, every single second of every single day, that requires an incredible balancing act.
Okay, now get this, because it's wild. Electricity isn't really stored in the grid. It's made and used at the exact same time. That means the amount of power being generated by all the power plants must perfectly, and I mean perfectly, match the amount of power being used by all of us in real time. If there's too little power for the demand, you get brownouts. If there's too much, you could literally fry the system.
So to pull off this amazing tightrope walk, the grid uses a whole team of different power plants. First, you have your base load plants. These are the workhorses, like big coal or nuclear plants, that run 24/7, providing a constant, steady supply of power. Then you have intermediate plants, usually natural gas, that can fire up or power down to handle the normal ups and downs of a day. And finally, you've got peaking plants, like a big dam, that can jump into action in minutes to handle those sudden spikes, like when an entire city turns on their AC during a heat wave.
And this all brings us to the great challenge of our time. This amazing continent-spanning machine was built for a world of a few big, predictable power plants. But as we move toward renewables like wind and solar, which aren't always on, the entire system has to be completely rethought. So the next time you flip that switch, just take a second to think about that incredible journey. And maybe ask yourself, what is the grid of the future going to look like?